almost look like, and if you were to cut them in half, this is what you'd see here at the bottom left. You'd see a nucleus, usually a detrital sand grain, around which several concentric layers of calcium carbonate have developed. And that grain structure is thought to arise from the competing constructive and destructive effects of calcium carbonate precipitation when the grains are at rest, and abrasion when the grains are transported, for example, in high energy shoals. So here we will test the hypothesis that sand is not necessarily generated only near the equator on Titan, but constantly regenerates through episodic abrasion when grains are transported and sintering when they are at rest, in a process that is analogous to the formation of ooids in Earth's shallow carbonate seas. And under this mechanism, grains are entrained and transported either by methane rivers or nitrogen winds. And as they get transported, they also abrade upon collisions, which will tend to decrease grain sizes through time. But when the grains are not transported, they may also sinter and coarsen through time. And this part of the process is a little bit different from ooid formation, obviously. We're not envisioning the grains to grow through precipitation here, but rather through a diffusion-controlled coalescence of small grains into larger grains over time. And as grains episodically sinter while at rest and abrade while in transport, episodic transport may then conspire to produce a sustained supply of sand-sized materials that maintain an equilibrium grain size. So the mathematical framework for our working hypothesis is relatively simple, and it states that grain size is set by the sum of abrasion when grains are transported and sintering when they are not, such that if grain size is at equilibrium, then the sum of the two terms here in the equation, bottom left, just must be equal to 0. So we'll consider the case of abrasion in both fluvial and aeolian environments, as both are known to occur on Titan. And the I term here in the equation is simply the transport intermittency, or the frequency of transport events. Okay, so combining these instantaneous rates with transport intermittencies, you can make predictions of what transport intermittencies are required, shown on the y-axis here, to produce an equilibrium grain of size of a given value, which is shown on the x-axis. The orange curve shows predictions for when transport occurs through 100% of transport driven by wind. And the blue curve is 100% transport being driven by fluvial flows, by rivers. And from both numerical global circulation models and observation from the Cassini spacecraft, the relative frequencies of winds and overland flows that could transport sand was constrained to be about 1 to 10% of the time, with the proportion at which transport could occur by winds versus rivers varying with latitude. Near the equator, if you remember, all transport virtually occurs in the aeolian environment, whereas the frequency of fluvial flows that are capable of transporting sediments increases near the poles. So adding our climate constraints here, we predict that 150 to 300 micron equilibrium grains should form near the equator, which is consistent with the optimal grain size for siltation on Titan. And we also predict the production of similar, perhaps slightly coarser sand grains near the poles, with equilibrium grain sizes around 200 to 400 microns. So what could this all mean for Titan's sedimentary cycle? We showed that a continuous supply of sand-sized materials could exist at equatorial and high latitudes, where winds or flows capable of transporting sand are relatively frequent. And we've shown that intermittent transport and sintering could lead to the formation of saltatable sand near the equator where the dunes are, and perhaps slightly coarser sand near the poles. Now, we also know that some sediments produced at high and low latitudes are transported towards the mid-latitude. As I mentioned earlier, the sediment transport pathways were mapped previously, and this was shown. And as ground moisture increases from the equator towards the mid and high latitudes, aeolian transport becomes less efficient despite relatively frequent winds, possibly creating a lull in transport frequency around the mid-latitudes. And sediments that accumulate then at mid-latitudes and aren't transported very frequently under our model could sinter into coarser grains and possibly even progressively experience diagenesis and turn into lithified rocks. So this mechanism could explain the formation of titans on differentiated plains, a scenario that is consistent with spectral observations that suggest a possible organic composition for large portions of the undifferentiated plains. And coarser organic sand grains produced at high latitudes could also eventually get deposited into terminal basins. This is where we have the lakes. And in the presence of soluble cements, diagenesis might occur as well, turning these sandy deposits into widespread organic sandstones, as has been proposed by Malaska et al. In 2020, which in turn could be responsible for the formation of Titan's karst-like labyrinth terrains. So to briefly conclude here, inspired by the mechanics of fluid formation, we showed that episodic abrasion and sintering of organic sand driven by Titan seasons could explain the latitudinal distribution of Titan's landscapes. Now, next, I will take you back to the inner solar system, closer to us, to think about the formation of rivers and landscapes that are devoid of plant life, and what it means for the landscapes of both the early Earth as well as Mars. And this work was conducted primarily in collaborations with Alessandro Yelpi and has recently been taken over by a PhD student in my group, Michael Hassan. So on Earth, we know that vegetation affects fluvial systems, the way they function and the way they get recorded into rocks. And notably, sedimentologists observe a dramatic shift in the architecture of fluvial deposits throughout the Paleozoic era. Fluvial deposits that predate the Silurian to Devonian periods typically consist of laterally extensive, relatively thin, but massive sandstones without significant floodplain mudstones. And in contrast, around the Silurian to Devonian periods, a lot more mudrocks appear next to fluvial sandy deposits. And fluvial deposits start displaying clear channel bodies, a lot more mud, especially in floodplain deposits, as well as what we call hydrolithic lateral accretion sets, which are these inclined layers of alternating sandy and muddy beds. And to date, these hydrolithic lateral accretion sets have been used as a diagnostic indicator of river meandering. And as a result, the transition that we see in the rock record was interpreted as a revolution in the planform geometry of rivers, with before the Silurian period, deposits were being interpreted as having been formed by wide and shallow graded rivers that have been called sheet graded rivers. And after the Silurian, observations were interpreted as indicative of the rise of point bar deposits, which are typically thought to be diagnostic of single thread meandering rivers. And interestingly, that fuzzy boundary where meandering rivers seem to appear in the rock record roughly coincides with the advent and diversification of land plants, going from the rise of land plants to the appearance of roots and leaves, to seeds, and finally to the appearance of trees. And in addition, many scientists have attempted to make rivers meander in the lab. And to this date, very few actually succeeded. Mainly those who did succeed did so by seeding their flume with alfalfa sprouts. So someone as far as saying that plants are required for rivers to meander, and that could potentially explain the transition that we see in the rock record. Now, something doesn't sit quite right with this hypothesis. If we look at Mars, which is the picture you can see here at the bottom, in which most realistically never hosted anything as complex as a land plant, we clearly recognize the deposits of meandering rivers. Not only we see these sinuous ridges, which are the remnants of amalgamated channel bodies, but we can even see evidence for lateral migration in the form of scroll bars and abandoned meander loops. So here, I will briefly show you how we have started testing 3 hypotheses regarding the formation of meandering rivers in unvegetated landscapes. Those 3 hypotheses are: 1, that plants made meandering possible; 2, plants affect the shape and dynamics of meanders; and 3, plants affect the deposits of meandering rivers. So the first hypothesis is that plants made meandering possible. Now, a corollary to that hypothesis is that meandering is not possible without plants. Now, here I'm showing a drone picture of the Amargosa River in Death Valley. And as you can tell, it doesn't bode very well for hypothesis number one. Here is another drone picture taken in the Columbus Basin of Nevada, in which you can see beautiful meanders and even a nice meander cutoff. Until fairly recently, modern unvegetated meanders had virtually gone unnoticed, largely because there are few and they're located in remote and arid basins. But today we understand that such systems are few, not because they cannot exist, but because it's just really difficult to find a place on Earth where there's no vegetation today. So today we've visited a little over a handful of unvegetated meandering rivers in the Western United States, namely the Mojave River of California, the Amargosa River, California, a few streams in the Columbus Basin, the McCloud Springs Wash in Nevada, Shoshone Creek as well, and Nevada, Twin River of Nevada, and a few washes in the Bonneville Basin. So although I do not really have time to expand on this point because I have a lot of other cool stuff to discuss, we developed a conceptual physics-based model for the formation of single-thread rivers in unvegetated but mud-rich substrates, and showed that single-thread rivers may indeed readily form in unvegetated landscapes, which is consistent with field observations at all of these locations. So our plans needed for rivers to meander. Again, I took a bit of a shortcut here, but I hope that at least the drone photos convinced you that the answer is no, and that mud and river banks can provide sufficient strength for flow to stay confined within a single thread channel. And that implies that meandering rivers should have existed before plants. We just really don't know how to recognize them. So, of course, that's a pretty important problem for the way we interpret the fluvial deposits of the early Earth as well as ancient Mars. So next, we tested hypothesis number two, which is that plants affect the shape and dynamics of meanders. To do that, we compiled the morphometrics of meandering rivers across the globe in both vegetated and unvegetated landscapes, spanning all climate zones but polar, as well as a range of tectonic settings. So starting with shape and specifically with the width to depth ratio of the river channels, here I'm showing channel depth as a function of channel width, with unvegetated rivers shown in blue and vegetated river channels shown in green. And essentially, we do not see any significant differences in the width to depth ratio of vegetated versus unvegetated meandering rivers. Now, we also looked at sinuosity and did not detect any significant differences. Next, we measured and compiled the lateral migration rates of both vegetated and unvegetated rivers from historical imagery, satellite imagery. And here the story is actually fairly different. Although both vegetated and unvegetated rivers display a clear correlation between migration rate and channel width, which you can see here in the plot, unvegetated meandering rivers migrate about 10 times faster than vegetated ones for a given channel width, almost a full order of magnitude larger, faster. So finally, the third hypothesis that we wanted to test then is whether plants affect the deposits of meandering rivers, especially if those unvegetated meandering streams migrate 10 times faster laterally. So to do that, and specifically, we wanted to see if we could identify any significant differences between the deposits of unvegetated streams and those of vegetated streams. So we've conducted field investigations of the deposits of such rivers in the Great Basin. Here I'm showing you a set of trenches that we dug at Shoshone Creek, but we've surveyed other areas as well. And so here I'm showing you one example from the trenches that we dug that nicely sums up most of the important aspects of what we saw. So at the bottom left, we can just see us actually digging a trench in a point bar and channel fields. This is an aerial picture taken by the drone. To the right, you can see what the trench looks like. At the top, panels A and B are looking downstream in the direction of the blue arrow or gray arrow here in the bottom left. And panels C and D are the photos and interpretations of a smaller trench that we dug in the streamwise direction. And the position of C and D is marked by in panel A by that dashed white line here. And all of the numbers that you see in those trenches correspond to the grain size distributions that are shown in panel E and F. Again, I don't have really time to discuss these in great detail, but I'd like to highlight a few depositional features that really caught our eyes. As expected, we found low angle lateral accretion sets, which are marked with LA here in the trench, in the annotated trench, and an asymmetric channel profile. What was more surprising, though, was this outer bank depositional element that is labeled DA here, that is abutting the cut bank, the outer bank of the paleo channel. And the reason why this is surprising is because obviously the toe of the cut bank is generally thought of as a region of erosion rather than deposition. However, similar depositional elements were found to line many outer banks in the modern channel and multiple river systems in the Great Basin. So we know that these are actually pretty common features. And finally, while we were in the field, almost all sediment appeared by eye to be roughly fine to medium sand. However, when we brought the samples back to the lab and we measured their disaggregated sizes, which again are shown in panels E and F, we were surprised to see such poorly sorted sediment ranging from clay all the way to fine sand. This was particularly surprising in the lateral accretion sets, since what we had thought were sandy deposits turned out to be composed of really well-mixed sand and mud, very poorly sorted sand and mud. Now, in addition to trenching, we also flew a drone. You've already seen a few pictures to get a better sense of the organization of the floodplain and map the floodplain. And notably, we found this is a mosaic of all of our drone imagery of the floodplain with the main channel and one of those systems. We found that abandoned channel deposits make up almost 50% of the modern surface, which is surprising from a relatively small stream that would normally be thought to migrate relatively slowly in relation to its to the rate at which it aggregates vertically. So this table here briefly summarizes important differences that we found between the deposits of vegetated versus unvegetated meandering rivers, some of which I didn't touch on as much, such as, again, homogeneous lateral accretion sets made of well-mixed, fully sorted mud and sand, some outer bank deposition, the DA element in the trench, subtle levees. That's the point I didn't really discuss. Levees are very, very subtle, impossible to detect by eye on the ground. We had to use very high resolution visual elevation models from LiDAR to actually detect anything, as well as cross-cutting amalgamating channel sediments, as opposed to the typical isolated channel sediments we see in vegetative meandering systems. So these properties altogether actually make the deposits of these single channel rivers somewhat more akin to those that have been typically interpreted as diagnostic of graded rivers than those of vegetated meandering rivers, which could possibly skew paleoenvironmental interpretations of the pre-vegetation rock record. This block diagram here is our new facies model for unvegetated meandering rivers, and it summarizes all of our field observations to date. Again, some of which I didn't discuss, unfortunately, like the crevasse clays and the rilling. And as a new facies model, obviously, it still certainly needs to be tested against examples from the pre-vegetation rock record, but this is a pretty good summary and synthesis of all of the observations we've made in analog systems, modern analog systems in the Western United States so far. So to briefly summarize, how do plants affect meanders in their deposits? Well, first we found that there's no significant impact of vegetation on channel geometry. However, plants slow down channel lateral migration by almost a full order of magnitude. And as a result, the deposits of unvegetated versus vegetated meanders look very different. And there's a typo here. It should say unvegetated meander deposits. should they actually display similarities with those of sheet braided rivers. So there's a possibility that we misinterpreted, or some deposits have been misinterpreted in the past. So going back to the broader picture here, again, our results suggest that there's no reason for pre-Silurian rivers to have been all braided, and different types of rivers almost certainly coexisted before the rise of land plants. We just don't really have tools to recognize them in the rock record, and our goal will be to develop such tools in the years to come. So this has profound implications for the way we approach paleohydrology on the early Earth, but also, and perhaps more importantly, on Mars. Now, because there is no plate tectonics on Mars, the remnants of billion-year-old meandering streams, some of the earliest sedimentary records that we have in the solar system, have been preserved, providing a unique snapshot of Earth's early meandering streams and their record. So back a little over a year ago now, the Perseverance rover landed in Jezero crater on Mars, where an ancient river once flowed into a lake and formed a delta, the Jezero Delta, the remnants of which you can see here. This is an orbital image of the delta. And on top of the delta lie the deposits of ancient sinuous channels that used to swipe across the delta top. And our findings about the deposits of unvegetated meanders have implications for the distribution of fine-grained sequences in the fluvial deposits within the delta, which in turn is particularly important because mudstones are thought to be good, if not the best lithofaces to preserve organics and make for very desirable astrobiological targets for the rover. So I'm very excited to see how the exploration of Jezero's fluvial lacustrine deposits unfold and how observed fluvial deposits compare with those that we've explored on Earth. Here I'm showing a figure from Mars 2020's very first science paper, which I had nothing to do with. It just came out, I think about 6 to 8 months ago, reporting on the distal stratigraphy of the delta as seen from a distance. This picture was taken over, I think, maybe not a mile, but over a kilometer away from the delta. The delta campaign is actually just starting right now. So very soon, we'll get to see these deposits and from up close, and I anticipate that they will really teach us a lot about how to interpret Earth's pre-vegetation fluvial record, again, once we get up close. So wrapping up with this example, Earth's pre-vegetation fluvial record is likely much more similar to Mars's than to the modern terrestrial fluvial record. But unfortunately, most of that record on Earth was lost to largely plate tectonics or altered by metamorphism and deformation, whereas it is still sitting at the surface of Mars in a near pristine state. So exploring Mars can really teach us about Earth's past in ways that Earth simply cannot anymore. And so finally, we are going to stay on Mars for a little bit for my third and last example. And I will tell you about how an observation we made on another planet taught us about a fundamental geological process, and that is the formation of sand ripples by winds. And this work is a result of discussions and collaborations with many people listed here on this slide. So when one thinks of a sandy desert on Earth, the top picture is kind of the mental picture that they build. We see large dunes mantled by small and decimeter scale ripples. Now on Mars, the picture is a little bit different. This is what we see here at the bottom left. This is a picture that was cropped from a mosaic of mass camera images acquired by NASA's Curiosity rover in Gale Crater when it crossed a field of basaltic sand dunes. And here to the right, I'm showing you the distributions of bedform wavelength or crest-to-crest spacing as observed on both planets. And on both planets, sandy deserts have a mode of bedforms with decimeter scale wavelengths. These are the small ripples that you can see in the pictures to the left. We also see 100-meter to kilometer scale bedforms on both planets, and these are the big dunes, like the ones that are shown on the right. But on Mars, we are left with this intermediate peak at 2 to 3 meters that corresponds to these large ripples that you can see here in the bottom left. These are nowhere to be found on Earth. And it's important to note that there are real gaps in bedform wavelength around 20 to 80 centimeters. And then again, between 20 to 80 meters, completely separating the large Martian ripples from other bedform types. They are distinct from the small ripples, and they are distinct from the large dunes. Now, in addition to having different sizes, they also look quite different from any other bedform. They can have sinuous crests. Some are asymmetric. They almost look like breaking waves on the ocean surface with kind of shallow upwind slopes and steep near angle of repose downwind faces. And they're often associated with grain fall deposits, which are these smooth blankets of grains that settle out of suspension past the ripples crest, and grain flow deposits, which are these little avalanche deposits that you can see here in the bottom left. So these large Martian ripples really are unlike any bed form that we presently have identified in our semi-deserts. So how do the large Martian ripples form? Well, on Earth, the formation of aeolian ripples is thought to be intimately tied to siltation, or again, hopping of sand grains through an impact mechanism. You can imagine that if you have wind blowing from left to right here over a bumpy sand bed, and grains are hopping around, then grains that are resting along the upwind facing side of a bump will be preferentially exposed to the potential impacts from incoming siltating grains and will thus preferentially be splashed away. Conversely, grains that are resting along the downwind side of a bump are located within a shadow zone that is cast by the bump's topography, and that protects these grains from being impacted and splashed away. And as a result, grains are preferentially removed from the upwind side of those bumps and accumulate along their downwind side, which cumulatively leads to the growth and migration of so-called impact ripples. Now, before we knew that small ripples also existed next to the large ones on Mars, it was actually thought that perhaps the lower gravity and atmospheric pressure on Mars led to longer siltation trajectories, and thus potentially could explain the longer wavelengths that we could see from orbit through a similar mechanism than these impact ripples. However, this single mechanism cannot explain the co-occurrence of both scales of ripples if they form in unimodally distributed or well-sorted sand. Another possibility is that the large Martian ripples are coarse-grained ripples, such as those observed by the Spirit rover, yet another rover at El Dorado, here shown in the top right, as well as by the Curiosity rover itself in a sand sheet outside of the dune field, as you can see here in the bottom. In both of these hypotheses, that the large Martian ripples are impact ripples forming in bimodal sand, or that they are coarse-grained ripples, requires the presence of a coarse-grained population. So to test that hypothesis, we took a closer look at sand grains with Mali, which is the microscopic imager on board Curiosity. So this is Curiosity here, taking a selfie in front of one of the dunes that we investigated. And you can also see, for example, the crater rim here to the left, the mountains you can see to the left. And that crater also has a central mound, a giant mountain in the middle of it. And this is the hill you can see here right behind Curiosity. So it turns out wherever we saw small ripples migrating on top of large ripples, which themselves piggybacked onto a larger dune, we found that sand that makes up these bed forms is actually relatively fine and well sorted. So we don't think that the large Martian ripples are either impact ripples or coarse-grained ripples. Now, there's another type of bed form that those large Martian ripples actually resemble, but those are not formed by winds, but instead by water on Earth's riverbeds, right? They look like subaqueous ripples. You can see here a set of current ripples in the top right picture that formed on top of larger river bars. They are asymmetric. They are sinuous, just like our large Martian ripples. Now, in water on Earth, they form at about 12 centimeter wavelengths, and they are distinct from dunes, fluvial dunes, which form at kind of meter scale wavelengths typically. Now, in contrast to the impact ripples formed by the wind, current ripples form from a hydrodynamic instability. As water accelerates upstream of a defect going upslope because of flow contraction, fluid drag causes entrainment of grains and thus erosion, while flow expansion past the break slope causes sediment deposition, which ultimately leads to the growth and migration of current ripples. Now, to investigate a potential fluid drag origin for the equilibrium size of large Martian ripples, we performed a dimensional analysis. So we thought about, okay, what are the parameters that govern the size of fluid drag ripples? They are grain diameter, D, the specific submerged weight of grains, RG, the shear velocity of the flow, U star, and the kinematic viscosity of the fluid, nu. And based on the number of parameters and their dimensions, one can show that the problem can actually be recast in terms of three-dimensionless quantities. And in fact, Mehmet Yalin in 1985 showed experimentally that that problem can be further reduced to only two-dimensionless quantities. The first dimensionless quantity that we chose to use is a dimensionless wavelength, here lambda star, which is defined as the wavelength of the bed form lambda, divided by the ratio of the kinematic viscosity of the fluid to the shear velocity of the flow, which is in turn a proxy for the thickness of the laminar viscous sublayer in the stream. So that number, lambda star here, the dimensionless wavelength, can also be seen as a ripple scale Reynolds number. Now, the second number that we chose is the Yalin number, which can be rewritten as a Reynolds number, where the length scale now, instead of being the sediment grain size, is the sediment transport saturation length, or the distance it takes for the flow to actually reach transport capacity. And of course, the formulation of that saturation length depends on the dominant mode of transport. So for subaqueous ripples, the dominant mode of transport is bed load, such that the Yalin number can be rewritten as a function of the particle Reynolds number and the Shields number of the flow. So again, briefly, for those of you who might not, remember fluid mechanics and sediment transport, the particle Reynolds number is a measure of how much grain sitting on the bed sticks out of the viscous sublayer. It's also a measure of how turbulent is flow past the sediment grain. And the Shields number, or the Shield stress, is a measure of flow strength relative to stabilizing gravitational forces. So here I'm plotting our dimensionless wavelength, lambda star, on the y-axis as a function of the Yalin number on the x-axis for a variety of different bed form types. Here I'm plotting current ripples on Earth in those blue circles, and you can see that they plot along a power law of exponent 1/3, which is shown by this line here labeled fluid drag scaling relationship. As expected, the Martian dunes here in pink and the small ripples in yellow plot off of this trend. Again, we know that these do not form through the same hydrodynamic or aerodynamic instability as current ripples on Earth's riverbeds. However, the size of large Martian ripples seems to be fairly well predicted by that same scaling relationship, which supports our interpretation then that the equilibrium size of large Martian ripples is set by a hydrodynamic mechanism that is similar to that that is responsible for the formation of current ripples on Earth. Now, this conclusion is further supported by looking at the distribution of large ripple wavelength globally on Mars in dimensional form. So putting everything back in dimensional space, here I'm plotting ripple wavelength on the y-axis as a function of atmospheric density here on the x-axis. And thanks to Mars's large range in surface atmospheric density today, we measured the size of ripples from the top of the largest volcano in the solar system all the way down to the bottom of the deepest impact crater on the planet. It's about 28 kilometers of elevation range. We were then able to actually sample ripple wavelengths that span over an order of magnitude in atmospheric density. And one key observation was that the wavelength of these large ripples actually does decrease with increasing atmospheric density. And furthermore, the prediction from our scaling relationship, which is shown here in the black lines, is actually matched fairly well by the data. Again, that same hydrodynamic theory that was developed for current ripples on Earth. Now, this is really cool because one can imagine that if those ripples get fossilized, turn into cross-stratification in sedimentary rocks, it may be possible to use those ripples as a proxy for paleoatmospheric density. So in order to use ripples as a proxy for paleoclimate, we need to understand how sediment translates into sedimentary structures in the rock record, and in particular, what is the stratigraphic signature or the cross-stratification that is left behind by those bed forms that we don't have on Earth. Now, the geometry of preserved cross-stratification is a function of the geometries and migration directions of the various scales of bed forms, as well as the rate of sediment deposition relative to bed form migration rate, for example. So here I'm going to show you an example of a sinuous bed form population migrating obliquely on top of the larger bed form, and the corresponding cross strata or cross sets that you'll be able to see in the cross section. It's actually an animation you can see it grade through time. And because of their high sinuosity and their relative scale, the large ripples are expected to leave those trough-shaped, kind of smile-looking sets of strata at sizes that are too small correspond to those left behind by the larger dukes. And if we find such trough-shaped cross-sets in ancient Aeolian sandstones on Mars, then we can infer the paleoenvironmental conditions under which the rocks were deposited. Because the thickness of those troughs scales with ripple height, and that ripple height scales with ripple wavelength, then we can use, again, the thickness of those trough cross-sets to invert for the wavelength of the bed forms that form them, and in turn invert, because the wavelength scales with atmospheric density, we can then invert for atmospheric density. So we actually did just that. We found preserved stratification from ancient large wind ripples on Mars. This is an example yet from another rover. This is the Opportunity rover, which visited the Burns Formation and Victoria Crater back in 2005, I believe. And based on the thickness of the trough cross sets that we observed at Victoria Crater, we inferred a range in ripple wavelengths that is shown here by the height of the red box here. And when combined with our scaling relationship, yields a range of atmospheric densities that actually strongly overlaps with the modern atmospheric density. So this finding was surprising and actually supported the idea of a thin atmosphere at the time of deposition of the Burns Formation sandstone about 3.7 billion years ago. Now we know that around that time, or maybe 100 to 200 million years before that, there still was water on Mars. And so this is actually a very interesting observation that really starts telling us about what happened to Mars's early atmosphere and how did it disappear. So this last example was an instance where the surprising observation from Mars actually challenged our understanding of one of the most fundamental sedimentary structures there is. Again, just sand ripples. Really illustrating how exploring other planets may allow us to probe unexplored parameter spaces and revise or refine our models for geological processes. So through this high-level kind of sample platter of some of our group's research, I hope to have convinced you all that a lot can be learned through comparative planetology. So first, drawing a comparison between the formation of calcium carbonate fluids on Earth and hydrocarbon sand on Titan allowed us to build a self-consistent mechanistic model for Titan sedimentary pathways in response to the moon's climate that is capable of explaining the distribution of Titan's landscapes. Second, we showed that the study of the early Earth, and in particular Earth before the advent of macroscopic life on land, could really benefit from the exploration of ancient Martian sedimentary deposits. And finally, by providing a full-scale experiment in which sandy deserts form under a low-density atmosphere, Mars kind of revolutionized the way geoscientists think about one of the most fundamental landforms there is, sand ripples. So to conclude, I will just say that quantitative models for surface processes developed from observations on Earth can be applied to learn about hydrology, climate, environments, and habitability of other planetary bodies. Again, this has been done for a few decades now. But in turn, the diversity of planetary bodies in our solar system really offers a wealth of new data that often challenges our understanding of geological processes. And it's really this dialogue between the Earth and planetary sciences that, in my opinion, offers one of the most exciting and promising avenues in the field of surface processes today and in the decades to come. So I just want to emphasize that through space exploration, we will be able to gather more and more data from extraterrestrial landscapes, providing a wealth of new information about the geological processes that shape the planetary bodies in the solar system. And to name just three here, I'm showing you artist renditions of the Perseverance rover, which again landed in Jezero Crater on Mars last year, and is there to look for signs of early life in the solar system. In the lower right corner, you can see the first woman and the next man to land on the moon near the lunar South Pole during the Artemis mission, which is currently planned for a launch in 2025, I believe, at this point. And in the lower left corner, you can see the little quadcopter named Dragonfly, which will be flying over the alien landscapes of Titan. This mission is a NASA mission, is planned for a launch in 2027. And we'll only arrive at Titan and land in 2036. So it's long-term planning here. And yeah, with that, I'd like to thank you again for having me tonight, and I'd be happy to take any questions.
Well, first, I want to check, Matt, can you hear us from the computer?
I can't hear you very well. It's yeah.
Let me put this. Put it back on the Mac microphone here. Okay. So if anybody would like to ask a question, please come up to the computer and speak.
Okay.
I can actually turn the camera.
I had a question about your third example with the ripples on Mars versus Earth. You had three equations. I'm not a sedimentologist, but I was looking for the G for the gravity. And I saw the third one had a gravity factor. And since Mars only has 40% of Earth's gravity, it seems to me that should have an impact on how the ripples form. And you did discuss that at all.
Sure. Let me bring back the slide. So gravity, actually, you don't see it in the equation here, but it's encapsulated in the particle Reynolds number and in the saturation length. So gravity is going to affect the not only the length, but also the height of the hops, the siltation trajectories, which in turn is going to affect the saturation length of the transport. So again, the distance over which sediment capacity is reached. And so gravity does come into play in that parameter here in the Yalin number. But it turns out actually.
So what is that impact? Does that mean that the Mars tend to have longer wavelength ripples for the same size grains?
Yeah, so we thought that might be the case, right? Before we actually saw the small ripples on the ground. But once we got up close to the dunes, the Curiosity rover, we saw these small ripples here. Now, because this is not a orthorectified picture, there's no scale, but perhaps here it is a little better because there's a rover for scale. So the rover is the size of a small SUV. The wheel is about maybe this big across. You can see this, there are small ripples and their wavelength is about 10 centimeters, maybe 8 centimeters, very, very similar to what we see on Earth. So somehow gravity does not change the initial wavelength of those impact ripples that much. Now, there are a few things that might be responsible for this. One is that the sediment on Mars is typically basaltic in nature, so the density of the grains will be a little bit larger than on Earth. Now, it doesn't make up for the difference between the gravity on Earth and Mars, but it does make the grains a little bit heavier relatively. But also, the Martian winds are pretty weak. So the wind speeds on Mars are going to be a little bit lower as well. So between that and the denser sediment together, those effects might conspire to make similarly sized impact ripples both on Earth and Mars, despite the lower gravity. Yeah, it's a good question.
Any other questions? Let me ask you one, Matt. I was intrigued by your comment towards the end that the thin atmosphere back at the time when there was still water on Mars tells us something about the way in which the planet was losing its volatiles and water at that time. Could you say a little more?
Sure, yeah. So actually, I didn't add a citation here, but so, this finding, this paper came out in 2016. Since then, the Curiosity rover has kept climbing. So the Curiosity rover landed in the bottom of the crater, and its goal is basically to climb up, not all the way to the top, but some distance up the central mound that is within the crater, because that mound is thought to be made of sedimentary rocks. You can see the layers from orbit. And it's thought that those sedimentary layers actually formed during the big climate transition of Mars, when we went from having a thicker atmosphere, wet surface environments, all the way to the modern, dry, arid, low density atmosphere environment. And so since 2016, the rover has climbed further up the stratigraphy, and so has moved away from the wet period to when that transition actually happened. And one really, really fascinating observation that we made is that we actually found stratification that was left behind by large ripples like these that are sandwiched, they're stratigraphically bounded by subaqueous deposits, both below and stratigraphically above. And so what that means is that there has to have been at least one episode of atmospheric collapse with the atmosphere kind of replenishing again before it collapsed and stayed thin over time. And this is super interesting because climate modelers there's a few papers where climate modelers have predicted that such periods of episodic atmospheric collapse might have occurred when Mars transitioned. The reason for that is that so Mars, of course, is fairly small. Has gravity about a third of the Earth, and it doesn't really have a magnetic field anymore. And so even though it had an atmosphere to start with, it's really hard for Mars to hold onto it. And so through time, the atmosphere has been eroding away. So it's been losing atmospheric density progressively through time. Now, Mars's orbital parameters, so its obliquity, for example, is pretty chaotic because of some weird resonance that happens with other planets. Very different from Earth, which our orbital parameters are fairly constant, and we're all very happy about that. But Mars is actually fairly chaotic. And so if you have oscillations in the obliquity of the planet, and you're getting close to a point where the atmosphere is thin enough that if you straighten the rotation axis of your planet a little bit too much, the atmosphere is going to collapse and condense around the poles. So basically the atmosphere forms CO2 ice near the poles. And then once you have a transition back into a more oblique configuration, that those polar caps might sublimate again, replenishing the atmosphere with CO2 episodically. And so such periods of atmospheric collapse might have occurred a few times actually, right when Mars was kind of crossing that threshold of atmospheric density. And that was only a hypothesis that was modeled by climate modelers. And thanks to the large Martian ripples, we now have stratigraphic evidence that it actually probably happened. And that it happened about 3.7 billion years ago.
Okay, I'm going to go ahead and stop the sharing so we can see your picture in full size here.
Okay.
This here. There we go. You're kind of frozen in time there, but we see your picture. So again, Matt, we want to thank you very much for joining us tonight. We appreciate it. And we'd like to see you in person one of these days. You can come and join us, have a beer, talk geology and geophysics up straight. So thank you again.
Great. Yeah. Thank you very much. Yeah. Thanks for having me. Thank you.
Okay, I'm going to stop the recording now.